Okay, so next up are chemical reactions involving gases. And as I mentioned before, this is going to combine information associated with our ideal gas law use with stoichiometry and with using balanced chemical reactions. And so the first example that we're going to go over is a modified version of a slideshow problem. There's one little detail that we're not going to go over this semester that I took out. So please just make sure you kind of focus on the information that I'm giving you here. All right. What we have is a solid that's decomposing, and it's decomposing into sodium and nitrogen gas. This species is sodium azide. Now, azide is N3 minus. You don't really need to know that, but if you're looking at this and saying, oh my goodness, I know sodium must be plus one, so, oh, is this really a polyatomic ion? And the answer is yes. It's three N's stuck together that have a total charge of negative one. So sodium azide can decompose and you can get solid sodium metal, not charged sodium, just sodium metal, and you can generate nitrogen gas. Okay, so now this is a reaction that involves a gas. So here's some information for you and then a question to answer. What happens if we have 50 grams of our sodium azide and we're reacting it to form nitrogen, and then we measure that nitrogen, and the nitrogen is 299.15 Kelvin in terms of its temperature. It has 720.3 millimeters of mercury of pressure, all right? And we're asked to get a volume. Okay, so now here's the thought process. What happens when you have T's and P's and V's that you're supposed to interrelate with each other? Okay, you know that we're going to use the ideal gas law. PV equals nRT. But now let's do our little checklist and analysis of the things that we're given and what we're trying to calculate. So we're given a P. Now we're given a P in the wrong unit, so we'll have to do a conversion to the correct units. Okay, but that's something we can definitely handle. V has to be our unknown, so everything else we have to know. Well, we've memorized R and we're given a T. So here we have an issue because it looks like there's two things we don't know. It looks like in terms of the nitrogen that's being made, we don't know its volume and we don't know its moles. And when we have one equation, we need just one unknown in it. And in fact, our unknown has to be volume. So how can we use other information given in the problem to calculate these moles? And we go and we look and we say, well, hold on. The thing we didn't address yet was how many grams of solid were involved in this reaction. Now, when I use the ideal gas law, it refers to gases. So if I'm giving grams of solid, is that the N in here? Well, no. Everything here has to be about the nitrogen that's generated. But if I know information about one chemical species and I'm asked to get information about another chemical species, right? Do I have a method that I've practiced over and over again that allows me to do that? And the answer is yes, right? If I know I have 50 grams of sodium azide and it's going to completely react to form nitrogen gas, right? You can use a balanced chemical reaction to take grams of sodium azide and make it moles of N2 generated. And then once you do that, you now have N as a known value. And then once it's known, V is the only unknown. So then we just pay attention to units and significant figures like we always do, and we can answer this question. So it's a two-step process. Let's do a conversion problem, like from a previous chapter. Let's get a value for moles, like from a previous chapter, but then let's use those moles, all right, in the ideal gas law and get information, right, volume information for nitrogen in this new way that we've developed this chapter. So I look at this reaction and I notice it's not balanced, okay? So one of these situations where just for extra practice, you can take a second and pause the video, try to balance it yourself. And balancing this involves knowing that there's three N's here and two there. So we could think about it in terms of a common factor. What's a common factor of 3 and 2? It's 6. So if I put a 2 here and I put a 3 here, then I have my nitrogens balanced, but my sodiums won't be balanced in this case. So I have 2 sodiums here, so I can finally balance it by putting a 2 there. So now I have a balanced chemical reaction. So can I take my 50.0 grams of NaN3 and can I convert it, I need moles of N2, can I convert it to moles of N2? And that's something you all should have confidence in doing, right? I need the molar mass of NaN3, right? And so when I look at the periodic table and I do that, I get 65.02 grams of NaN3 for every 1 mole of NaN3. Now, this isn't a limiting reactant problem. In fact, there's only one reactant, and it completely goes away to generate nitrogen, right? So we know we can just use the mole-to-mole ratio at this point. And we could say, well, there's 2 moles of NaN3 for every 3 moles of nitrogen that we generate. And so when I plug this into my calculator, what I get out is 1.15349 moles of nitrogen. Oh man, now I know everything about nitrogen. I know its pressure, I know its temperature, I know the amount of moles, so I'm able to solve for the volume, okay? The one thing that we have to do, is my temperature in the correct units? Yep. But is my pressure? No. So I have to take this 720 millimeters of mercury and turn it into atmospheres. And so let me do that here. So we know there are 760 millimeters of mercury for every 1 atmosphere. So when I do that, I get a pressure in atmospheres, I should say, that is equal to 0.9477632 atmospheres. Pay attention to significant figures. There would be 4. We don't round yet, though. So now I have all the information I need to get volume. So I can plug everything into the ideal gas law with the correct units now and get a final volume, okay? And so please do this yourself. I'm going to leave this step out because I want you to practice using the ideal gas law, but realize you have everything you need. You have your N, you have your P, you have your T, and you can solve for V. And paying attention to significant figures, what you get out at the end, and please confirm this, is 29, right, 0.9 liters of nitrogen. So that sodium azide, when it disappears, and when I use the ideal gas law, it generates a lot of nitrogen, 29.9 liters of nitrogen. Okay? So this is one example that deals with gases and also combines our stoichiometry skills. Make sure you understand it. Ask questions as always. I want to do one more example just to show you that even limiting reactant problems can come to bear or can come to play when we're dealing with gases now, right? So let's look at this example, which involves the formation of water. So we have this reaction where we have hydrogen gas and oxygen gas coming together to make liquid water. This is a formation reaction. We'll kind of talk about that in the next video set, so don't worry about that quite yet, but it is interesting to see that, yep, we're forming one thing, we're forming water, okay? Now I'm going to give you some measurements that we took, okay? So in terms of O2, right, what we did is we looked and we analyzed it at STP, and we measured its volume to be 2.19 liters. And we did the same thing with H2. We measured its properties at STP, and we also developed 2.19 liters of H2. And now we're going to mix these two together, okay? And what our question is how many moles of H2O liquid do we make? So how does this fit a limiting reactant problem? Well, you're given information about one reactant, and then you're given information about another reactant. And what are you trying to do? You're asked to make a prediction. So we follow the same sort of rules that we have for limiting reactant problems, but if you think about what you need, right? If I have O2 information, what do I need to get to H2O information? I need a mole-to-mole bridge. Oh, so if I can take this information, I can get moles of O2, Then I can use my mole to mole bridge that's here, and I could get moles of H2O. But I won't be done, because I know for a limiting reactant problem, there are two conversions I need to do. So I could also get moles of H2, convert over to moles of H2O. And then what do I do for a limiting reactant problem? I pick the smallest, okay? And that's exactly what we're gonna do here. So eventually, like, it kind of feels exactly like problems we've done in the past. The extra step is realizing if I'm giving a temperature, a pressure, and a volume, I can use the ideal gas law to get moles. And if I'm given a temperature, a pressure, and volume, I can use the ideal gas law to get moles. And then I can finish the problem in a normal limiting reactant way, okay? How am I given a temperature, a pressure, and a volume? Remember, STP translates into very specific values, right? So let's do this, all right? Let's set this up and let's work it out completely, but hopefully you understand, based off the information given about each gas reactant, we're able to enact a limiting reactant process. So let's look at O2 to start with, all right? So if I have a pressure of oxygen, a volume of oxygen, number of moles of oxygen, and R and T of oxygen, all right, I'm able to get the number of moles of oxygen, okay? Well, we're told standard temperature and pressure. So we know that the pressure of oxygen is 1 atmosphere. And that's a definition, so we know it is just a value. 1 atmosphere is not going to affect the significant figures in our problem. We were told that we had 2.19 liters of oxygen, right? So we write that in there. The number of moles of oxygen is our unknown. R is always 0.08206 liter atmospheres per mole Kelvin. Oh, and that reminds me that my temperature has to be in Kelvin. So even though I know STP translates into 0 degrees Celsius, we know we have to add 273.15 to it to get it to Kelvin. So the final value here that you'll be able to fit into your notes for temperature is 273.15 Kelvin. Again, that came from the definition of STP, so significant figures are not going to affect that value either. So whatever I get out for number of moles of oxygen, I'm going to be limited to 3 significant digits because of that measurement there. So when I do this math, right, what I get for the number of moles of oxygen is 0.977037 times 10 to the minus 2, right, moles of oxygen. Now we could do the same thing for hydrogen, but this is an interesting problem because if you think about your setup for hydrogen, what was the pressure of hydrogen? Well, it was 1 atmosphere because it was measured at STP2. What was the volume of hydrogen used? Oh, it was the same, right? So we could redo all this math, but it had the same temperature, the same R, the same volume, the same atmospheres. Our information about H2 is exactly the same. So we kind of recognize that as a special example where we can see that. It won't always be the case, but like I said, you would use your skills if there was any difference. You would use your conversion skills. You would use your ideal gas law skills to recognize what the moles of hydrogen are. But for this particular problem where the volume was the same for oxygen and hydrogen, why not just like skip doing that math because we already know what it's going to be. Okay, so now, all right, what we're left with are moles of oxygen and moles of hydrogen, okay? And what do we get to do to finish off a limiting reactant process? Well, to finish off a limiting reactant process, right? Ooh, sorry, I wrote these wrong. Please make this correction here. Let me look at my notes quick. Give me 1 second, sorry about this. Yeah, sorry about that. Okay, so I don't know why I wrote the scientific notation incorrectly. Hopefully you caught this in your own. I honestly didn't do it on purpose. Sorry about that. These should be 9.77037 times 10 to the minus 2 moles of oxygen and the same number of moles of hydrogen. Sorry for writing that incorrectly. Okay, So now with these values, to finish off the limiting reactant process, we're asked for moles of H2O. So what we can do is we can use our balanced stoichiometric coefficients, right? 1 mole of oxygen would produce 2 moles of H2O. So when I do that math, okay, what I get is 0.195 moles of H2O could possibly come from the oxygen. So let's do the mole-to-mole relationship here. 2 moles of H2 make 2 moles of H2O. So that's like multiplying by 1. So in terms of the H2 conversion, what we get is 0.0977 moles of H2O. At the end of a limiting reactant problem, which one do we pick? We pick the smaller amount. And so we're not asked for grams of H2O. We're not asked for atoms of atoms inside H2O or molecules of H2O. We're asked for moles of H2O. So at this point, we are done. So let's just recap this problem. We were given H2 information. We could use it to get moles of H2 using the ideal gas law. We were given O2 information. We could use it to get moles of O2. All right. They just happen to be the same for this problem. Right. Moles of each reactant can be converted to moles of product. And then, as always is the case for limiting reactant problems, the smaller amount tells us the information that we're going to pick at the end of a limiting reactant process. Okay. So again, it's just coupling information that you already know to ideal gas law information, but I thought it worthwhile to show you a couple examples just to make sure you're completely comfortable with it. The next video that we're going to do is going to deal with other types of gas law problems that are new. But again, if you kind of get what we've done so far, we'll adhere to the same principles, keep the correct units, make sure we understand our definitions, and pay attention to significant figures along the way.